So, good morning everybody, and today all of the time will be taken up by a long case study, namely binary search trees, or as much as we can currently do with binary search trees, because our ability to write complicated proofs is limited by what we know so far. No? Right. Now, we need a little bit more data types before we can formalize the binary search trees properly, and we need the type of sets. Now, I will come back to sets again in the next lecture, but here I will just briefly introduce the basics. So the type of sets over a component type A is written A set, like the lists, and we have all the usual set theoretic operations, elementhood, union, and other stuff, and we will just need, I guess, these two, in fact, in what comes. And we also have a special form of quantification, universal quantification over sets. So I will also use this formula for all elements A in a set big A, some property P is true. And luckily, the proof method auto knows at least a little about sets, so we don't have to know how sets behave, and we don't have to use specific lemmas about sets from the set theory library, but for the simple things that we're doing, auto will know all about that. Right, so question about sets? No. Then the focus, well, not just of today's lecture, but quite a bit of the lectures to come will be on binary trees. And there is already a library that we'll be building on, and this is the path to the library. So what is this tilde tilde? You use that path when you include a file, or you import a file in your header, and this tilde tilde tells the system this is the location of your Isabelle installation, and then it's inside in the logic HL, in its library theories, there's a theory called tree. So this is, in fact, when you include it, you don't write the dot theory. I think I should probably remove that, otherwise it's confusing. When you actually put that into the import section, we will see that in a moment, then you never mention the theory extension. Now, what's in there? I don't want to go through the whole file, there's quite a bit of stuff in there, but I will just mention the key things that we need. And the most important thing is, of course, the definition of the binary tree itself. So it's a data type with two constructors, leaf and node, where the node, the order of parameters is first the left subtree, then the element, then the right subtree. And we use abbreviations, at least sometimes. Sometimes I write things out, sometimes I abbreviate them. So this is just a short way of saying leaf. And it's not really shorter. Well, it looks shorter, but when you type it in, it takes a bit longer to type. And therefore, I often type this, and then the system, at least in its output, shows me the short version. And nodes are written like this, again with these angular brackets, and then just comma separated, the left subtree, the element, and the right subtree. So this is special syntax introduced for trees. And now I will just familiarize you with the basic functions on binary trees that we'll be using in the case study. So first one is size. What's the size of a tree? And intuitively, it's just the number of nodes. So that means the size of the empty tree is 0, and the size of a tree with a node, L and subtrees L and R, is just the size of the two subtrees added together plus 1 for the node. And another important function is in-order listing of a tree. I always think of it as a projection, so you have this two-dimensional tree, and then you project it onto the x-axis. That is just a recursive function that walks the tree, and for the empty tree you get the empty list back, And for a node, you take the e-node of the left, then the element, and then the e-node of the right. Remember, this is the append function on lists. What else is there? Yes, the elements of a tree. So the elements in the nodes of the tree. That's important information about the tree. So we have a function set underscore tree. So there are various set functions that, given some type, produce elements of that element, or given some container, produce the elements in that container. And typically they are written set and then underscore, and then comes the type of what kind of container you are taking the elements of. And here you're taking the elements on a tree and get a set of elements back, and the definition is exactly how you expect from the empty tree. There's nothing in there, so this is how you write the empty set. I didn't put that on the slide about sets, but I hope the notation is clear enough. If you have a node, you take the union of the left subtree, the right subtree, and a single element in that node. And I think this is probably the final one, a map function. So there isn't just a map function on lists, but also on many other types. And here's the map function on trees. So it takes a function from A to B, takes an A tree, and gives you back a B tree by applying that function to all the elements in the nodes. So it's a straightforward recursive definition. And here's the one for the node, where given a node and a function, you produce a new node where you've recursively mapped the function in the left and right subtree, and the element A is now being, the new element is FA. One last thing. Now we come to the case study, binary search tree. And by the way, when I say the binary tree library with binary in parentheses, that simply means that much of the time we'll be using binary trees, and I will just say tree, and implicitly it'll be a binary tree. So, of course, there are some exceptions when later on we look at more general trees, but for much of the time, it's all our trees are binary. So what is a binary search tree? Well, you know that quite well. This is the invariant of the characterization of a binary search tree. It just means it's ordered. The empty tree is a binary search tree, and if you have a node, then the two subtrees must be binary search trees, and for all the elements x in the left subtree, x must be less than the element a in the node, and for all the elements x in the right subtree, x must be bigger than the node element. So this is the characteristic specification or invariant of a binary search tree. Now, here's something interesting. Where does this less than come from? Why are we allowed to compare the elements of the tree for less than? Well, strictly speaking, we aren't, and there's something missing here, which I haven't shown. So this function doesn't work on arbitrary binary search, on arbitrary trees. So, for example, it won't work on trees where you have stored in the nodes functions, because you can't compare functions for less than. But implicitly, or it is, you have to state it explicitly, but here it's implicit. This type A is restricted to those types that do have a less than on them. And yeah, correct. This is, and this brings us to a topic that I'll just scratch the surface of, namely type classes. So if you're familiar with Haskell, then this will not be anything new to you, or just new syntax for something you already know, different syntax. So let me give you a one slide summary of what the Isabelle type class system provides, and at least it'll be enough for this course. So what is a type class? A type class is defined by a set or list of required functions, the interface. So you can think of that really as an interface in some programming language. But in addition, a set of axioms about those functions. So the type classes in Isabelle, in contrast to programming language type classes, do carry with them properties that the functions must satisfy, the functions in the interface. So please do not think class in terms of Java. Java classes are very different. Type classes are just interfaces with properties in Isabelle. And here is an example, not the precise syntax, but just in the system there is already predefined a class called linorder for linear orders, and those comprise all the types that have these two functions, a less than or equal and a less than on them, and order the elements in a linear fashion according to the using these two relations. Oops. And when does a type belong to a type class? Well, type belongs to a type class if it provides all the functions of the interface that the type class requires here, and if the functions satisfy the axioms that come with a type class. So in this case, in the class of linear orders, something is a linear order if it has these two functions on it, and if the two functions satisfy the axioms of a linear order. And at that point, when you want to convince the system that a type is in a certain type class, you really need to do a proof. And the notation, you can write type : class name, and that means the type belongs to a certain class. Here is an example of that, where you use that inside a type, that notation here. The full type of the BST predicate is not just a tree to bool, but it's A, where A has been restricted using this notation to come from the class of linear orders. So that means BST, the system will refuse to apply BST to any a tree of a type that is not a linear order. Questions about type classes? And I think throughout the lecture course, the only type class we will really need are the linear orders. Okay, then, that's just implicitly saying A must be a linear order. Well, not implicitly, explicitly saying it by putting this requirement on it. And now let's look at the case study. And this is where I switch over to Isabelle. That's not it. That's... Yes. So yes, here you see the import section, and we import that library theory and without the theory extension.
I have a question.
Yes.
Can you also just write tree?
You can, but then it won't find it, because if you write that, then it'll assume that the tree is in the same directory as the BST demo.
Okay, because if you can import main and things like real, and so they are.
Yeah, because you're starting. By default, you're starting from an image that already has all of that loaded. So you don't have to load it. So all of these names are known, but this is not part of the image that you start from. So you explicitly have to give the path to it. This is something that I'm not even sure we really need. Yes, we do need, but it's generally useful. This line says, please always use the definition of the let construct as a simplification rule. That means when you have a term containing let and you simplify that term, then the let will disappear, and if you have let x equals t, then the in t prime, then the x will always be replaced by t in the t prime. So that may cause some blow up, but in general, it's what you want to happen in proofs, and it's even debatable whether it should be a default. It's not a default, but for this course, I think it's a good idea to make it, to start your file with that, if you have let constructs, otherwise it doesn't concern you.
How do you manually unfold it?
Simp, add, let def. So now let's just define the most basic functions on search trees, namely the isin function that searches recursively down a tree and tries to find an element. And this is of course, the interesting part, the node. You compare with the contents of the node, and if the element you're searching is less than the contents of the node, you go recursively into the left subtree, otherwise you go into the right subtree. And the third alternative, of course, is because we're in a linear order, then x and a must be equal, and you can return true. Of course, you could you do the order of comparisons in a different order and use first compare for equality. This is just one particular way of doing it. And the next one is the insertion function. How do you insert into a tree? Again, not again. The type now the ins function takes an element, a tree, and gives you the new tree back. And so if you insert into an empty tree, you get a tree just with that element in it. And if you insert into a node, it's the same game as before. You have to check whether your element is less than the element in the node, bigger than, and if it's equal, well, then nothing happens. You basically just return the same node that was given as an argument here. So this is our starting point. Not too complicated, but now we're going to build things on top of it or modify and provide variants of this. And the first thing we do is we prove its functional correctness, right? So do these functions do what they're supposed to do? And yes, they do what they're supposed to do. So what are the properties that you would have to prove for a binary search tree? Well, a binary search tree implements a set, at least with this interface that we have, where we can just test for elementhood and put something into it. And therefore, we need to show that this is a correct implementation of the test. And so this is the theorem you'd have to prove, that the isin function does the same thing as if you take the elements of the tree and then you just check that the given element is an element in that set. And unsurprisingly, this is just an inductive proof over T. So the only point here is really to show you this lemma, to show this is the correctness lemma for the isin function on trees. So no matter how complicated it is programmed, this is what you'd have to prove about it. And similarly, for the insert function, you also have to show whether that function is correct. So that's the correctness statement about the insert function. If you insert an element into the tree, and then you take the elements, the set of elements in that new tree, well, that should be the set of elements in the old tree union the x that you've just added. That's again the requirement that you should put on the insert function in a binary tree. And of course, if it were a delete function, then you would have to remove the x from the tree. And note that in one case, we do explicitly say, we assume that this is a binary search tree. We need that, of course, because otherwise, if it's not a binary search tree and you rely on the ordering, then you could claim that an element isn't in the tree, although it is in the tree because it's in the wrong part of the tree, because the ordering is screwed up. Yeah.
Should you also prove for functional correctness that insert x maintains the binary search tree?
I wouldn't call that functional correctness, but that's debatable. In my terminology, functional correctness just means that the interface functions do functionally the right thing, and then separately you have to show the preservation of the invariant. You can also say that's part of the functional correctness. I don't know. That's not a clear-cut division. So now we also have to show, as was suggested, that the insert function preserves the invariant. And as you can see from the sorry here, this hasn't worked. So what's the problem? So we do an induction on T, and we do auto, and right, we are left with, in fact, two sub-goals. And now, to make it interesting for you as well, not just hear me talk all the time, why didn't it work out? What additional property is probably required here? A property that we may already have. Or rather, can you point to a term that's sort of in the way? Yes?
I think it should be the insert lemma.
Yes.
Insert something that would be in the set of the tree.
Yes, because the system has not simplified this term here, but we know that this should be the union of X and the sets of elements in T2, and maybe that helps. So what we should do, we should go back. This is the name of the lemma, and use that lemma and see if it helps. And it does help. Yeah. So that's typically the thing you do. You look at your goal, and if there's something that you think should be simplified further but hasn't been simplified further, either you need to use some lemma that's already in your theory, or you need to invent a new lemma. So that went rather smoothly. Now, the next one is a bit trickier. I want to reduce the number of comparisons, because if you look at the code here, you do in every node 2 comparisons. But wouldn't it be nice if we could do one comparison? But of course, if we assume that there is a comparison function that gives you 3 results less than, equal, or greater than, then the problem is solved. But we are assuming we only have the less than and less than or equal and equal comparison. So how can you get away with just one comparison per node? Well, you have to be a bit, there's a trick there. And it's not clear to me that this trick really buys you much, because you have to pay for it in another place. So the trick is the following. If X is less than A, well, you can go into the right branch, into the left branch. Of course, if it's not less than A, then it's greater or equal. So you don't know, is it equal or is it greater than? And what you do is, at that point, you say, oh, well, let's not do this test now. Rather, what we do is we just go down the right branch and accept the possibility that maybe we missed this element. But then we additionally carry that element with us, so that if we go into the right branch and find, oh, it's not there, then we check, oh, maybe is that one of the ones where we made sort of an optimistic guess and go into the right branch. So we carry with us an additional argument in the is-in test that says, this is the last element where I may have gone wrong and where I forgot to test for equality. And then when I find I'm at the bottom of the tree and I haven't found the element, then I'll compare with that element that I'm carrying around with me. And so now we are going to put that function together. So I can show you the type of the function already, but no more than that. And here is in words what I already said. So the function takes a tree, and it takes an A option, so it takes an optional element, and that's the element where we forgot to test for equality when we went down the tree, and it's optional because we start with none there. Remember, the option type had these two constructors, none for nothing and some for one element. And so that's why it's optional, because in the beginning we don't have anything, but at the first time where we meet a node and go right, although we don't know whether the element we have is maybe actually equal, at that point we have to set that parameter. And then when we get to the bottom of the tree, we have to test for that parameter if we haven't found the element. So, is in 2 of some node LAR and some element X equals, okay, so as I said, we make a case distinction. If X is less than A, well then we're okay. Then there's nothing, oh sorry, there's a parameter missing, it's the tree, this optional element, let's call that Z, and then the X we're actually searching for. Then we definitely need to go into the left subtree. And, well, the Z will stay unchanged because we haven't made a wrong decision recently. So it's the same place, it's the same element where we went wrong the last time, or possibly went wrong the last time, and we're still searching for X. Otherwise, we call is in 2 as well, but now we go into the right subtree and still search for X, but what should be the middle argument? Yeah?
Some A.
Some A, indeed, yes. Because we remember, we in this sub call, if we don't find the X in there, well, maybe it was the A and we just forgot to test for equality. So this is where we get where we put the sum A into it. So now comes the base case, is in 2 of belief, and Z and X. And here well, I could have made the case distinction on the left, but I'll make it on the right. We make a case distinction on the Z. Case Z of none. What should we return then? A Boolean value is called for here? Yes?
False.
Then it's false. We definitely haven't found the element, because even on the way down, we never remembered any element. And otherwise, if it's sum A, then what should we return? Yes. Then you return the comparison of A and X. Yes?
So I have a question. Maybe you answered it before, but doesn't it mean that you cannot terminate early? So you always have to walk through to the leaves?
Yes. That's true, but on the other hand, most of the elements are at the bottom of the tree. Half the elements are at the bottom of the tree. So that I think that efficiency or inefficiency is not too bad. What is, of course, costing you more, at least in a functional language, if the compiler isn't optimizing it well, is that you have an additional parameter. So now you have to pass more parameters in each recursive call, unless the compiler sees, oh, well, this parameter doesn't change, and so I can. I think this will not really buy you. I haven't timed it, but I don't think it will really buy you much in a functional language because it'll. Well, hang on. It is now tail recursive, so maybe actually the compiler will turn it into a loop and will realize that this parameter just gets updated some of the time. So maybe actually it does buy something. It's not clear. It depends on the compiler. Pardon?
So it might be better.
It might be better if the compiler. Yeah, so it's one of those things where, and that's in any high-level language, you have to rely on the compiler to do the right thing. You're not really at the machine level, and you can't control things so minutely. But yeah, you'd have to time it and see what happens. Okay, so that's the code. Here it was, sorry, Z, and here it's, what is it? Some A, I think. And here it's false. And here it's X equals A. Oh. Something's what? Variable A occurs. Oh. Yeah, some A, sorry. Yeah, so I've called it Y there, then let's call it X equals Y. Yeah, thanks. Okay, now here's the first attempt. This is what you really want to prove about this function. That if you pass in counterexample? Yes, no. Is there anything wrong with the code? This isn't directly provable, as we'll see, but wrong. Let me just get rid of this. What's the claim here? Is in two claims. Oh, right, yes, of course, it is wrong. That was intentional. There's something missing. What's missing? In the statement of the theorem. Yep. Yes. Okay, first attempt. So now there are no more counterexamples. We do an induction, we do auto, but we can't get the theorem. In fact, there's a lot of stuff that's been left unproved. So let's just look at the very first one, and then you won't see it. But if you look, well, actually, if you look at the first subgoal, you will see it already, and it's pretty obvious. The first subgoal already asks you to prove something about a call of is in 2, where the parameter is sum. So just proving something about the none case is too specialized. You need to generalize. Now, we don't generalize. We can. It's enough to get. We can get away with proving the two cases separately. One lemma for the sum and one for the none case, and that's what we'll do. So we'll move this lemma up here. So this is the lemma for the none at the sum case. So let's look at the lemma. It says if you have a BST, then, well, this should be the same. Is in 2 with sum should be the same as is in, and it's clear that that can't quite be, because this here, this Y has no influence whatsoever. So there's something, and in fact, AutoQuickCheck found a counterexample. So this isn't quite right. We need to prove something more specific, in fact. So when we have, yes, we need, and that's why we have the parentheses here, the square brackets, but we need something else, some other assumption that will always be true when you make a recursive call with a sum in it. Then that element Y has a certain property that we will need in the proof. The element Y and the elements of T will need to be in a certain relationship. Yes?
On the right side of the equation, there is a Tx. Another possibility is that epsilon equals T, Y equals T, sorry.
Yes. Actually, I think there are two problems here, and I was trying to fix one, but I think it's more important to fix the other one. So how do you extend the right-hand side?
Or Y equals T.
Y, x equals y. Right?
Yeah, X equals Y.
Yeah, or y equals x, whatever.
Y equals
Yeah,
X,
yeah,
not T,
yeah. Mm-hmm.
Yes.
So that is the first fix we need. The second fix is we need some more assumption about the y. Yeah.
The Y is greater or equal to X.
I think that will not be sufficient. Let's try. Y is greater or equal x.
Or smaller. Not greater or equal.
Okay. Y is smaller than x. But then we would never need the test x equals y, if we assume that. Yeah.
Y should be smaller than every element of T.
Yes, that's it. So this is where we need the for all. So if you type an exclamation mark, by the way, it'll give you a menu item to convert it into the universal quantifier. So for all, I guess we call it Z. Do we call it Z? Oh, we can call it X. Nah, let's call it Z. Z, and the element sign can be replaced by, the colon can be replaced by an element sign. Z in the set of elements in T, we have that way around?
Yes.
Yes, at least that's what my notes say. So why is that true when we look at the recursive call? If we look at the call here with some A, then we know this A is less than, because this A comes from here, so it's definitely less than everything in R, and that's exactly the T that we have. So it is guaranteed by the recursive call, so it's okay to assume it, because in the inductive case, it'll always be in that situation, and we will always have that property. And now I think we are already there. Let's see. Auto. Yes. And so you see, it's always, you start with something quite simple, and then you have to generalize it. You have to gather additional preconditions to make it true, and eventually you get there. And note here just with the arbitrary why do we need that? If you look at the definition, what is this y? The y is the contents of this parameter, that this memory, or whatever you want to call it, and that changes in recursive calls. If you look at here is in 2, then the second parameter can change in a recursive call, and therefore we have to generalize over it because it doesn't stay fixed throughout the computation. So now we go back to our initial attempt, and this is really the main theorem that we want to prove, that if you put in none, then it does the same thing as is in, and we do an induction and we do auto, and it still doesn't work. But now, of course, we haven't used this theorem, so we explicitly use this theorem. And if we look at the situation where it gets stuck, we do have assumptions of the right form. So we do have these assumptions for all x in a tree, something is less than, something else is less than. So we will be able to use this lemma, which in itself has one of those assumptions. So the assumption will be automatically proved by what is available here in the list of assumptions. So yeah, now it goes through. Okay, so this was this little trick. And now I want to extend our tree with size information. So I want to store in every node not just some element, but also the size information about that node, and that will be helpful in a function that we program later on that needs the size information all the time, and you don't want to then recompute it all the time. So there are two ways of how you can store this additional information in the tree. One is you define a new kind of tree that has an additional field, and that has advantages. And another possibility is that in your element in the tree, you don't just store the element, but you store a pair of the element and the size. And this is slightly slightly simpler, and that's why I will go for that solution. But making it a separate field is perfectly fine. It's just not the way I've chosen to do it. So here I introduce a new type, namely tree underscore sz for size, and that will be an ordinary tree, but the elements in the tree will be pairs of the actual information that you're storing and a natural number, the size of the whole node. And then we will definitely need an invariant about the size that says in this tree every node has the correct size information, and that's just a recursive definition. Of course, a leaf always has a correct size information, and a node where in the middle you have this, no, wrong one, here we are, where in the middle you have this pair AS, there the S must be the correct size. So on the right we say, of course, left and right must have all the sizes correct, and the S must be the sum of the size of L and R and 1. So that's our nice recursive invariant. And we also define an auxiliary function that simply extracts the size information from a node, but you don't have to distinguish the node. Well, from when you call it, you don't have to distinguish whether it is actually a node or a leaf, because we just define the size information of a leaf to be 0, and of a node, you just take what's in the node as additional information. Right. And we introduce yet more notation. The function unsize just takes the size information out of every node, so it takes one of those trees with size information and gives you back a normal tree. And I will just make this an abbreviation. The unsize function is simply an abbreviation for map first over the tree. So everywhere you apply the first function, which you haven't seen yet. So what is FST? If you type term FST, it tells you FST is a function from A cross B to A, and it's not very difficult to guess what that function will be doing, because there isn't really much of a choice you have when you want from a pair to produce something of the type of the first argument of the pair. You have to take that element.
Do we define the size function somewhere?
The size function is predefined. We're using it here, but it's in the library about trees. So you have to distinguish the size function, which simply treats this as an ordinary binary tree and counts the nodes, and the sz function that reads out the element information. And here in the invariant, we require that the size function, which is in the library, is in fact that the size field is the same as the what the size function would give you. So first, what is this? Oh, insert, right. An insert function now which maintains the size information in the nodes. So do we need more space? No. Oh, no. Yeah, it's practically everything is visible. So if you insert an element in the leaf, you create a node with the size information 1. And if you insert something recursively into some node, and let's just look at the case where the element is less than the element in the node, well, then you insert in the left part, and you call that L prime, the new left part, and then you create a node of this form of the new left part, and then inside the element A that was there before, and now you recompute the size information for that new node, but there's really not much computation going on because the function sz simply takes the information from the two subtrees and adds it. Of course, you need to do that. Why can't you just take the old size and add 1?
There's a possibility that the element already is in one of the subtrees.
Yeah, so that's why you have to do it that way. Okay, so now functional correctness first. Does the insert function on with the size information, does that still do the correct insertion operation? And so this is how we describe this, and maybe a diagram will help because this is one of those nice commuting diagrams. We have two kinds of trees. Here we have the normal trees, and here we have the trees with size information. And this lemma that you see at the bottom of the top pane says, well, if you take a tree and you insert with this insert size function something into it, then you get a new tree. Well, that's this, and now you delete the size information from that new tree. So you take the unsize function. That's the same thing as if you had deleted the size information right away and called the old insert function on ordinary trees without size information. So this is a standard way of proving some refined version of a data type correct, that you have an abstraction function that takes you from the more concrete version where, for example, you store additional information back to the abstract type, and then you show, well, it doesn't matter if I execute my function on the concrete level, my interface function, and then abstract to the abstract version of the, in this case, the tree, or if I first abstract and then execute the corresponding abstract function that we have already proved correct. And that works very smoothly here. At least I hope so. Let's see. Yep, that worked without any complication, induction, auto, then it's done. But now we have to also show that the invariants are preserved. So, and there are two invariants. There's the binary search tree invariant and the invariant for the size contents. So let's start with the size one, no, with the binary tree one. I claim that if I start with the tree T with size information and I remove all the size information, and that is a binary search tree, well then if I insert something into that tree T and then remove the size function, the size information, then it's again a binary search tree. So we didn't redefine the notion of a binary search tree on these trees with pairs in them, but we simply locally use the unsize function to get us back to the abstract level, and then use the binary search tree predicate on the abstract function, on the abstract level. So this should be just a simplification, but it isn't. So if you apply simp, it just says I can't do anything. So any suggestion, and we just need things that we already have. What should we? What simplification rules should we be using here? So we don't need an induction. So what else could we be using or needing? Well, there is one lemma here that tells us something about unsize of insert size, and that's exactly what we have here, unsize of insert size. So it's maybe useful to use that lemma. Right. So now, what could be useful in order to solve this one? Something we already proved. It's just a special case of something we proved. Namely that a certain function preserves a certain invariant. Yeah.
Insert preserves the binary.
Yes, and it just looks more confusing because instead of an arbitrary tree T, we have on both sides the unsize of T. But if you ignore that, then it's exactly the lemma that we proved further up. Where are we? Here. There we are. It's a special case of that lemma, that BST is preserved by ins. Where are we? So let's add that one as well. And yes. This is just a shorthand for writing apply and then writing done. You can write by. So now we also need to show that the size information is updated correctly. So if the size information was correct in the first place and you now apply the insert function, it's still correct. So do an induction on T, auto, and yep. We don't get there. So what is missing? In this case, we need another simple lemma in order to make progress with even the first subgoal that you see here. And there's some subterm that should alarm you. Yes. Let's look at this line. That's what we have to prove. That line is almost the identity, but not quite. Why not? Where's the problem? Why isn't it the same on both sides? Yeah?
We have to show that SZ is the same as the size function with the invariance.
So we haven't proved that yet, and so we need to prove that, and I will just move that little lemma up. Oops. So we need to show that if the invariant, the size invariant is true of T, then the SZ function of T is in fact the size. And since this is really something you would always want to be using in the context of this tree, I've made it a simplification rule. So this goes through without any problem. And now the next one, I think, also went through. Yeah. And now we didn't include this size information for nothing, but we will be using it now because I want to provide an additional function on these trees that says, please give me the nth smallest element. And there it will turn out to be useful. So the nth min, I've called it here. That's the nth smallest means the one at the very left of the tree would be the 0 smallest, and the next one, if you think of the projection, would be the 1 smallest, 2 smallest, and so on. And this is what we want to compute now. So we can, I think, go one. Yes. So at the bottom you see nth min of L and AS and R. And we want the nth minimal one. So how do we do this? Now we don't compare elements. We have to compare sizes. So when do you think the nth minimal element is in the left subtree? Yeah.
When the size of the node is greater than the n.
At the end, right. So since we will be using the size of the node a few times, let me abbreviate that. Let size of left is just SZ of L. In what? Okay, so I guess the order doesn't matter, so let's take it in the order to start with it. If n is less than the size of the left subtree, then we simply recurse into the left part. How about the n? Does that need to be changed?
No.
No. Okay. Next case distinction.
If they are equal.
Yeah. If n is equal to SL, well, then we found the element. Then certainly it's the element, I guess A is called. A, yes. Now, then, of course, it must, in the third case, it must be the right subtree. Which n? Yep.
N minus SL minus 1.
I think so too, yes. Because you've dropped all the elements in L and you've dropped all the and that one element A in the node. Yep, that's it. So, do I really want to type this? Apparently I do. Yep, so let size left equals size of L in if, let me write it like I've got here, n equals size, no, SL, then A, else if n less than, I'm just reordering it, n less than ESL, and then nth min of L and n, else nth min of R and n minus SL minus 1. Oops. Yep. Okay, function definition completed. Now, I want to show that the function does what it's supposed to do, and I've already indicated we're searching for the nth element in the in-order projection of the tree. And this is exactly what the theorem here tells us, if it can be proved, that taking the nth minimal element in the tree T is the same as first getting rid of the size information. So now we have a normal binary tree. Then we take the in-order traversal of that. So we now have a list. And now we take the nth element. So nth is a predefined function on lists that gives you the nth element given a list and the n. So if you click on it, then you can be taken to its definition. And there you can also see that it has the following infix syntax. So it's an infix exclamation mark between the list and its index. And that's why if you look at the output, you see on the right-hand side this exclamation mark. Let's try our luck and induct on T with an arbitrary n, because that n changes. And of course, I've done those proofs, and I've noticed that we need an additional lemma, namely nth append, that is already in the library. So here's a lemma about append and the nth function. If you take the nth function of an append, it's the same as making a case distinction. If n is less than the first part of the append, then it must be in that first part, and otherwise it must be in the second part minus the length of the first part. So you can see there's a certain similarity to the computation of the nth min function on trees, and that's why these two functions fit together well. But this is a lemma that you didn't have to prove, that the system, but that we already provided. But unfortunately, the proof doesn't quite go through, and the reason is that we need one more assumption because we are left with a subgoal that is a bit problematic. What's problematic about the subgoal? It's asking about the nth element or the nth minimal element of an empty structure, the empty tree or the empty list. Now that's not I told you everything in HOL, it must be a total function. So even the nth element of the empty list has some value, but we don't know which value it has. And so it is best, if you can, to avoid that. And how do we avoid that? Well, we simply require the n to be greater than 0. And so, no, I don't think that's what we want. We want the n to be less than the size of the tree. Remember, we start indexing at 0, so it's less than the size rather than less than or equal the size. And with that additional assumption, it now goes through. So this is, of course, a natural precondition that if you're asking for the nth minimum element of the tree that doesn't have that many elements, that you can't expect a sensible answer. Or you'd have to program some, then you'd have to work with some and none again in order to distinguish whether you get a real result or some degenerate result. So, are we doing? Yeah, we can do this one as well. Compressing the height of binary search trees. This is another simple application. So you all know with these unbalanced binary search trees, there's always the danger they degenerate. And here we just want to compress them a little, and we want to take care of a situation where the tree has degenerated into a list or a structure that resembles in large parts a list. And so this is what the compress function does. It takes a tree and gives you back a new tree. And, of course, it shouldn't change the order of the elements in the trees, but it should make them, should reduce the height, actually, if possible. And this is the main clause. So if you're trying to compress a node where the left subtree is a leaf, then you see, there's some potential compression possibility. Why? Because if you have this situation, node, and here you have a leaf, and another node, let's call this one A, there's A in there, there's B in here, and here's again a leaf, and some tree T down here. What can you do in order to get a tree of smaller height? Of course, you can rotate the tree a little bit and get back A, B in the middle, T here, and two empty trees. Like So this is what this function, this compress function does, except that it doesn't do it quite so naively, because then it would just look at the topmost ones and see the two leaves. What it does, it first looks at the top one and says, okay, that's a leaf. Let's see if we can compress this one and then get again something that's has a leaf here. So we first compress the subtree, the right subtree, and if that again gives us a leaf there, then you can combine these two subtrees A, B into what I sketched there on the board. And if, on the other hand, if that subtree after compression isn't of this form anymore, then there is nothing you can do at the top level anymore. And in all other cases, you simply go into both subtrees and compress them, and in a leaf, well, you can't compress a leaf. That's just the same. So this is just some quite naive attempt to reduce the height of a tree. Later on, I think we will look at a balance function that takes a tree and completely rebalances it so that the height is as low as possible. That's much more complicated. This is just a very simplistic approach. Now, what do we need to prove about this function? We need to prove that it preserves the binary search tree property and it doesn't change the set of elements in the tree either. And a very compact way of proving both things at the same time, I mean, they won't be trivial corollaries, but you can prove both of the preservation of these two predicates. They follow, and that should be intuitive, from proving this property, that if you compress a tree, then the new tree, the in-order of the elements must be the in-order sequence of elements must be the same as the in-order sequence of the elements of the original tree. That will give you both properties, that you've not changed the set of elements in there because the lists, the in-order projections are the same, and it will tell you if you started out with a binary search tree, then the in-order projection was sorted, and if you now compress and get the same in-order projection, well, it must still be sorted. And therefore, you must still have a binary search tree. And so this is a convenient way of proving two things at once. And unfortunately, it doesn't quite work here. What's the problem? We don't get very far at all. We've got two cases, a nil and a node case. The nil case goes away, but the node case doesn't go away. Why not? What are we doing wrong? What else could we be doing? And there's something problematic with the induction. Yes, you need the induction rule for the compress function, because the compress function is not primitive recursive, so it has a much more special recursion pattern, and therefore you should use that recursion pattern. And so you just say rule compress.induct, and then you should be getting three cases, because you have three equations defining compress, and indeed you have three cases. Let's not look at them in detail. Let's just do auto, and now we've just down to one sub-goal, but that one hasn't been proved, and it looks ugly. What does a short look at this suggest? What should we be doing, just intuitively? How would you intuitively progress with a proof like that, where you're trying to prove? Yeah,
you have to do case distinction.
Yes, you have to distinguish, well, what is this compress of T? What is the form? And there's this special option for the auto proof method, you can say, please split all the case constructs about the let's look at what is this case construct. It's compressed T, so it's a case construct over trees, and so we want to split all the tree case constructs, and this is the magic incantation you need to remember. So whenever you see that you're left over with some cases in your goal, then it's time, or it may be time to say, oh, please automatically also split all the cases that concern this type. And in this case, it's the type of trees. So you need to look at it before you do the splitting. You see, oh, there's a case construct over type X. And then you say, oh, please split X dot split. And there is an additional variation of this, because it may be that the case doesn't occur in the... This is the most widely useful form, but it may be that the case, and it only splits the case constructs in the conclusion of your proof, of your subgoal. It leaves the premises alone, because many times it would not be a good idea to split those cases as well. That often does more harm than good. So this is a heuristic. But sometimes you do want also the cases and the premises to be split, and then you can say tree splits, then it'll do both splits in the premises and the conclusion. You can only automate so many heuristics, and here we have to know about the fact that the system will do some things automatically, but not others. But here we didn't need it, because if you go back to this situation, if you look at the subgoal, the case only occurs in the conclusion. It occurs to the right of the arrow, and so we can just use the standard tree split, which just splits the conclusion. Now, I think actually, if we had defined... No, forget it. Yeah, forget it. Here we're trying to prove that the height of the compressed tree doesn't increase. It only goes down. And that goes through automatically with the same technique that we just had. You use the special induction rule for compress, and you split the tree cases. And that's not too surprising. You can look at your function definition and easily see, it won't increase the height. So this is not... it's not completely trivial. You have to go through various branches and see what happens, but it's no big deal. Now, this is a more interesting question. What we proved is that the height doesn't increase, but it should decrease. Well, it can decrease, but how much can it decrease at most? So, what is a lower bound for the height of compress of T? You can look at the function again. Or the diagram. Yep.
Log of the size of the tree.
That is certainly a lower bound, but I think we can do better than that. So that is a very optimistic. You'll never get to log. The compression that this compression algorithm gives you is much lower, much worse than log. It's just a factor of 2. The height can at most decrease by a factor of 2. So this is wrong. Instead of dividing by 2, I'll multiply by 2 on the other side. And indeed, I'm in the wrong lemma here. What is the lower bound on the height of compressed T? And you could divide it by 2, but I will instead multiply them by 2. And indeed, there are no more counterexamples found, so it looks like it's probably reasonable, but that's a little challenge to actually prove this. I got stuck with it, and it needs to be generalized in a clever way in order to be able to prove that. So if you try to prove this, it just won't work. You need to do some additional case analysis, essentially. But I'm not going to tell you. But this is something else you might try and prove as a challenge. Right. So then we come very nicely to the end with some extension from sets to maps. So most of the time, all the time so far, we use the binary search trees as an implementation of set, where we could just ask, is an element in it or is it not in it? Often you want to use such a search tree as an implementation of a map where you can say, please, which element is this element associated with? So this is what we do now with this lookup function. It now takes, again, we have a choice, how do we implement this? We could implement the fact that there is an association of an element, a key, and a value. We could implement this as an additional field in the tree. Then we would have to define a new data type of trees with one more field. What we do instead is we use, again, the trick that we make the element in the tree a pair, namely a pair of an A and B type, and we demand that the A is a linear order. The first component, the key, is linearly ordered, and of course the values, it doesn't matter what, there doesn't need to be any element, any order on it. And then the lookup function is very much the same like the isin function, except that it also returns an element, and it returns an optional element, because it might be that the key is not associated with any value, and then if you get to a leaf, you have to return none, and otherwise you go through the tree, and if you find the element, then you return some B, where B is the element associated with your key. So I'm sure you've programmed these things before, so that's not particularly challenging. And then there is a corresponding update function. So this is the generalization of the isin function, the lookup function, and the update function is the generalization of the insert function. So now the update function has this type. It takes two elements, a key A, a value B, and then it takes a tree and gives you a new tree, which has this additional association in the tree. And so if you update a leaf, well, you simply create a tree with that pair XY in it, and otherwise, well, it's the same recursive structure, so I don't really want to go through every line here. So now we need to prove functional correctness, and the first question is, what is functional correctness for this map implementation? And I'm not going to prove this in any way, but it turns out that you can characterize maps by, if you just have lookup and update, then this is the characteristic equation that these two functions should satisfy, that if you first do an update and then a lookup, well, that depends. If what you're looking up is what you just updated, then you get some of the of the value that you put in. And if it's not, then you look up in the original tree before the update. So this is the characteristic property that you need to prove. However you implement maps, if you have a lookup and an update function, this is the property that they should satisfy. And this goes through very nicely. So the functions are easy, the proof is easy. Now we want to show that the invariant is also preserved. So now what is the invariant? Again, we could even define an abbreviation here, but we make it as a definition. We go back to the binary search tree without any value, just the keys. And how do we do that? Again, by by mapping the first function over the tree, it deletes all the keys and you're left with the values. But I don't think that's what we want, is it? The keys should be ordered.
Yeah, you get the keys.
You get the keys, don't delete first.
Oh, sorry. Yes. Everything is fine. I don't know why I wasn't thinking. Okay, so you forget the second part, and therefore you just left with the keys. And now you have to prove that this new invariant on the maps is preserved by the update function. And this, I think, doesn't go through very nicely. So we do an induction, and we do auto. And the induction is still just on T because both lookup and update are primitive recursive over T, so there's no special recursion principle that you should be looking for. But still, it doesn't prove it automatically. And so we can now, we can see what the problem in the first subgoal is. That should be provable. Why isn't it proved? A very simple omission.
I think because the omissions don't get simplified.
Yes, so we explicitly need to say simp and then bst1 def. Okay, that has helped. Now we still haven't proved it. There's still some ugly looking subgoals. So let's focus on the first one and let's see if there's anything in addition that we may need to know. So in fact, it is a lemma that's missing some property of the functions that are involved. Which formula do you think is too complicated and should somehow be simplified? That's not completely obvious. So, yeah. Let me see one arm. Can we have a second arm? Okay, so what do you think? Where should we simplify?
I think if we do the map tree first and pass the update tree to it, it's the same as if we call it insert only with the text on the tree.
Yep. That's precisely it. Here, this subterm, you update the tree and then you map first over it. Well, then you basically, the update just becomes a normal insert because you're getting rid of all the values, and that's a useful property to have. So that's in fact the property that you can see creeping up here. I hope you didn't just look at that. So let me readjust that. So this is the lemma that mapping first over an update is the same as mapping first over the argument of the update and then inserting an element. Because the map first has basically on the left-hand side dropped the y, and you don't need the complicated update. You can do the much simpler insert. So your one motivation for why we're using that lemma and why we're using that lemma in this direction is that we're reducing complexity. We're going away from the complex update function to the simpler insert function. And that may or may not help. Of course, that's not a guarantee. This goes through automatically. Now we add this also as a simplification rule to our original proof, and that still hasn't done it. Oh, there's something else missing. Okay. So we need another lemma, and I think this is one that we already have. Yeah.
Probably that inserting maintains the element.
That's inserting?
Maintains the element.
I don't think that it no, I don't think it is that one, but that could be one. Let's add it. So I think that was BST ins. I think it hasn't helped at all, or did it? Let me see. It's still 2 sub-goals. I think it hasn't helped, but it was a reasonable guess. Something else. Yeah? Yep, that's what we should be using. So I think it is called that one. It is called set tree ins. So, except that we need to make it one name. Hey, what is this? Okay. Yes. So that was the missing lemma, and now it went through automatically. And wow, perfect timing. End of the case study, end of the lecture. So this was the first introduction of binary search trees. The material itself will hardly have been new to you, but I wanted to really go through a sequence of such proofs to emphasize the main points in induction and in dealing with cases and things like that. And let me just come back for half a minute to the slides. So, yeah. This was easy, but of course it's not a coincidence. It took me some time to find exactly these examples that were easy. So I chose easy problems, and difficult problems or more complicated code will need more than just saying, oh, induction and auto. And so what the next 2 lectures, next 2 or maybe even 3 weeks will be about more automation and a more expressive proof language. The automation will help to some degree, but much more important will be the expressive proof language, where you can really write down proofs that have internal structure, where you can go step by step and outline your argument and not have to rely on the prover to find all of these case distinctions or whatever you need to make automatically. So that's the end for today, and looking forward to seeing you next Friday.